Dear anaesthesia, please can someone explain what on earth is going on in this graph, because it makes no sense whatsoever. Absolutely. Start with our axes, and we're going to label them. On the x-axis, we've got right atrial pressure, and this is essentially the same as preload, so some graphs call it preload, because the right atrial pressure is a measure of how much fluid is going to go into the ventricle, and therefore it's a measure of how much fluid the ventricle has to work with. So it's essentially the same as preload. And then on the y-axis, we have cardiac output. Now, assuming you are not bleeding to death or being infused with life-changing amounts of fluid, that's going to be the same as your venous return because it's a closed system. So the blood leaving the heart should be the same as the blood returning to the heart. So cardiac output and venous return are the same. And what we're going to do is put onto this set of axes two separate graphs. The first one looks quite familiar, and it's this one. This is really simple, and you already understand this because you use it in your clinical management. This is saying, as I increase right atrial pressure, or as I increase the preload, the cardiac output is going to increase because I'm giving the heart more fluid to work with. This is why you give fluid in low blood pressure, because you think the heart would benefit from a bit more preload. And this is the graph's shape. It starts by being very responsive. So this is your fluid responsive zone. As you give more preload, as you increase the amount of fluid you're giving, the contractility of the heart increases. It's got more fluid to work with. This is your fluid responsive section. Then you reach a plateau. At this point, the heart has enough fluid, and the amount of preload is no longer the limiting factor on cardiac output, and so the actual benefit of giving extra fluid tails off. And so here you've kind of got your fluid responsive limit. From here to here, this is a fluid responsive area, and here onwards, there's no point giving more fluid. So this graph is more intuitive, and it's a good place to start. Basically says, as right atrial pressure, or preload, increases, the cardiac output is going to increase, and assuming you are not bleeding to death, your venous return will increase as well. That's the first graph. Now the key is, this is the independent variable, this is the one we're changing, and this is the one we're measuring as a result. For the second graph, we swap this around, and we're going to say this is now the independent variable, and this is the one we're measuring. And we are just superimposing these graphs for convenience. And the second graph looks like this. And for this graph, instead of saying cardiac output or venous return, we can say systemic flow. So we've drawn our cardiac function curve, and this is our vascular function curve. And what this is saying is, as our systemic flow, as our blood flow in the system drops down, fluid is going to back up into the right atrium and the great veins, and the pressure is going to increase. So it might be easier to switch it this way. So as flow is decreasing, the pressure is increasing. And this makes sense because if you've got cardiac failure, you're not clearing your preload, you're not pumping your fluid forward, so it all backs up into your lungs or into your venous system, and you get distended jugular venous pressure. You can see that as the flow drops, the pressure increases. The confusion from this graph comes from the fact that this one is, as this function changes, what happens to this one, and for this graph, it's as this function changes, what happens to this one. So this says, as you give more preload, the heart's going to pump better and it's going to increase your cardiac output. This one says, as your cardiac output drops, fluid's going to back up into your right atrium and your vena cava, and that pressure's going to increase. And if you get to the point where there is no flow in the system at all, you've got a completely stagnant system, once your flow, your cardiac output, hits zero, your right atrial pressure is going to reach a point, and this is your mean systolic filling pressure, which is the pressure in your system at standstill. So if there's no flow, what is the pressure that just sits in your veins? So that's why these two graphs are in these two different shapes. As you increase the fluid you're giving to the heart, it's going to contract more efficiently until you get to a plateau and you don't want to give any more fluid. And if you don't have decent cardiac output, then fluid's going to back up and the pressure in your right atrium is going to increase. Now I've redrawn this really simply just to demonstrate the intersect point. Here is our vascular function graph, and here is our cardiac function graph. Now this intersect point is where your heart ends up working for the following reason. Now let's say, for example, you have a dodgy beat, a strange ectopic, something, and your cardiac output momentarily drops. On this graph, you're going to go down this way because this is your systemic flow, and we've said that because your cardiac output has dropped, your venous return or your systemic flow is going to drop. And as a result, you're going to slide down this curve, and this is your right atrial pressure. So your right atrial pressure is going to increase. If your right atrial pressure is going to increase, that's actually going to drive you back up this curve, and it's going to increase your cardiac output on the next beat. So you end up with this sort of negative feedback, self-limiting process, whereby if you have one bad heartbeat and your cardiac output decreases, your right atrial pressure will increase, it'll increase the preload for the next beat, and it will bring that cardiac output back up again. Likewise, if your cardiac output increases, so let's say you have one really strong beat, you're going to go this way up this curve because you've got more flow, and therefore there's going to be less backup into your right atrial pressure. So your right atrial pressure will decrease, and as a result, because there's less preload on your next beat, it'll bring your cardiac output back down again. So you end up with this lovely negative feedback, self-maintaining system where you end up hovering around a set point. That's what that point means. And basically this position will move as you change different parameters. For example, if we increase the resistance the heart has to pump against, so we've increased peripheral vascular resistance, for example, by giving a vasopressor, our graphs are going to change shape and this point is going to move. So our graph of cardiac function is going to change to this shallower shape if we increase the resistance, because for any given increase in preload, you're going to get less cardiac output purely by virtue of the fact there's more resistance. You're not going to get quite so much flow for any given amount of preload. So this is the dashed cardiac function line here. At the same time, for venous return, for any given flow through the system, if you've got increased resistance, then the amount of return to the right atrium, and therefore the right atrial pressure, is going to be lower. And so that's why this point then drops. This graph has changed shape and coming down from here, and then your cardiac function graph has also dropped. So your intersect point drops down, showing that you get a reduced cardiac output if you increase the resistance. And it's the same in the opposite direction if you reduce the resistance. And that is how you end up with this graph shape. And hopefully that makes a bit more sense.